and thanks a lot for the invitations. Yeah, I was already introduced. So let me quickly give you the overview. This is a joint work with my friend Afshin in University of Portsmouth, and I'm working in the Ginkiewicz Center or Ginkiewicz Institute for Modeling, Data, and AI. This is a quick outline. Okay, there will be some motivations for why you want to work on the hyperelastic material with rate-dependent effect. And I will talk about the existing modeling framework, especially for viscoelastic material, and then a little bit details of the hyperelastic model that we will focus here. And then the model will be extended to incorporate the rate dependency. And then I will show you a couple of validation examples that nicely fit with experimental data from a wide range of soft materials, and then the talk will end by conclusion and outlook. So the rate effects or time-dependent effect of soft material is everywhere, right? For example, if you see in the top figure, this is a wave generator, a wave energy generator. So this is soft material. This is rubber-like materials, for example, natural rubber like this. You can strain as you like. And this is the laboratory material. So the wave is coming, and that will inflate and deflate the soft membrane. And when the wave is coming, it will deform, and the pressurized air here will try to move around. That is connected to the turbine that will rotate, and it will generate the energy. And then again, when wave will disappear, the air will come back and inflate the system again. So you can think about recent 3D printed tire that is produced by, or at least designed by Michelin in France. The other companies trying to follow that trend. That is called airless tire, right? And it's use of sub-material, right? And you can think about it experience rate-dependent behavior. Or if you think about the so-called metamaterials or different type of design for using in vibration control or other areas, definitely this type of sub-material will experience rate dependency. Or even artificial valve, right? So this is a few examples. If you go a little bit further, you know, the Adidas, Nike, and all these big companies are producing nowadays the 3D printed metamaterial structure with the soft material, and that will experience a rate-dependent effect. Or if you think about the human tissue, for example, a cartilage replacement or the vertebral replacement, displacement, or even flexible electronics. So you can see there are increasing amount of application of soft materials in different areas, ranging from traditional area, for example, the tire, to biomedical area, and where we have been using hydrogel or elastomer or extremely soft materials. And these conditions, especially if you think about the skin-mounted sensor, and if you do the sports and all these things, and that type of flexible sensor will experience dynamic effect. So definitely we need to take into account the effect of the time. Okay, so let me go back to some experiments. This is a customized experimental facility in my lab, and that can do experiment extremely soft material like human tissue, right? So if you have machine in your lab and you said, okay, I have very good lab install machine or Swick machine in my lab, and you take this type of submaterial or this type of submaterial, and you will not get any data because the load cell that you have in the lab is high of 7 kilonewton, 10 kilonewton, 20 kilonewton, and you will not get any response from this type of submaterial. Right? So what I did, I made my own tensile machine that can do extremely. So this is some sort of hydrogel, okay? And if you elongate 10 times or 15 times, you can elongate. And here we have a load cell that can sense 1 Newton load, okay? That means you can play with the extremely sensitive material. And then, what I want to do, so I know most of the submaterial, most means 99% or 95% submaterial will show you rate-dependent behavior, time-dependent behavior. So, and some people will argue this is the viscoelastic material. So, in order to identify a material as a viscoelastic, we need to do 3 types of experiments. One is called strain rate dependency. So, you pull the sample slow, fast, and faster, right? For example, here I did the experiment of 0.01 per second up to 0.05 per second, and different strains. So this is lambda 1.5 means 50%, or lambda 3 means 200%, right? And you can see if you increase the strain, the curve, and later it will be very important for the modeling. You see it goes down and then goes down and goes up, right? So the shape actually is giving you extreme nonlinear behavior. But the main message here, your material responds with time, with the strain rate. So it's not hyperelastic material anymore, right? Another experiment is called relaxation or single step relaxation. So you have a material like this, you pull it and you hold it. And then you see the load cell, and then you will see the load is decreasing because of the relaxation, right? So this type of experiment you need to do to understand whether the material is plastic, viscoplastic, or viscoelastic, or hyperelastic. So this is the second type of experiment. So if you're interested, that was my first paper in experimental mechanics or experimental area. Before that, I always did everything computational. And then another type of experiment is called multi-step relaxation. This is also relaxation, but you are doing the relaxation test on the same material in multiple times. So strain it, wait for, and then again wait for some minutes, go and wait for some minutes. So 50%, wait for half an hour or 1 hour, depending on the relaxation spectrum of the material. You need to wait for 5 hours, 4 hours, or even 1 day, right? And then you will see the relaxation in every step. So why we need this? Because we need this point, because this is a hyperelastic point. When the relaxation is finished, this material became hyperelastic, right? So this point is very important for my model fitting. So somebody come up with a hyperelastic energy function on the model, and they don't have any data, right? So many people use my data in the last 10 years, 12 years, okay? Okay, so this is multi-step relaxation data. So now we understand, if you do the rate dependency, strain rate dependency, material responds with different stress or different force. If you do the relaxation, either single step relaxation or multi-step relaxation, you see clear relaxation with the amount of time. Okay? So no way this is a hyperelastic material. And in my experience last 12 years, I never see any pure hyperelastic material, either of the phenomena. Either it has significant amount of relaxation, or all of them, or at least strain rate dependency. So let's focus on only on strain rate dependency. So before that, if we look into the literature, I think Yasmin will argue, okay, there are a lot of integral type model and this model and fatigue model. I don't want to argue who won what type of model, but I want to say one type of model is you have the energy potential, and that depends on your deformation gradient or right Cauchy gradient and something that depends on time. So this is A1 to AN, the so-called internal variable that depends on time. So you go to the classical approach of decomposition, you have the volumetric isochoric split because you need to take into account the incompressibility and so on. And then isochoric part will be split into elastic and viscous part. So the viscous part depends on time, right? Because as you see, if you stress it, and then if you wait, if you wait with time, you will see different behavior. So definitely in your modeling framework, you need to have something that depends on time. C doesn't depend on time, right? Then, but A depends on time. So in order to evaluate A on time, you need either an integral equation or differential equation. So basically, some people are coming from integration, some people are differentiation, but whatever, it depends on time, right? Some people say, oh, scalar variable, vector, tensor variable, Doesn't matter. For my case, I took a tensor type internal variable. It's a common framework. It's in last 30 years, people have been working in this area. I don't want to argue with the model, so I feed with the data. Then during the COVID period, just before the COVID period, I did experiment with other material. And very interesting phenomena I observed. It's published in Nonlinear Mechanics, and it was one of the highly cited and downloaded paper for 4 years. I don't know why. The reason is, you can see here. So it was up to 300% and up to 400%. And you can see not only rate dependency, it shows significant dependency on strain and strain rate, because the curve here, it goes up, goes down, and more or less at the plateau. But here, it goes up, goes down, and again goes up. So this type of behavior is extremely difficult to capture by the model that I have shown you. What I have shown you here, in this case, this is relaxation time, that doesn't depend on anything. So it is a constant parameter, and you can feed with experimental data. But later I realized, so no, the curve is changing. It's not only the strain, not strain rate, but also the strain. So if you go higher strain, you are getting a different curve. So I look into the literature, and some people say, okay, this is called nonlinear viscoelasticity. Okay, fine. So what to do? And then I changed the tau with respect to strain and strain rate. Okay. So now you see I can nicely capture the trend, which was not possible using the model that I showed you earlier. Okay, so this is the introduction, I should say, the experiment and the modeling approach in traditional viscoelasticity. But the problem is, in order to capture this extreme data, we need to have 18 parameters. And if you do the fitting with MATLAB or other software tool, if you have increasing amount of parameters, it's extremely difficult to get unique parameters. You will be fine. You say 2, 3, 4, 5 is fine, but not 15, not 20, right? And you will be facing problem to predict to validate the model. So if you look into the literature, if you summarize, I'm talking about viscoelasticity and including the rate dependency. Viscoelastic modeling here include basically the rate dependency as well, but also relaxation. So you say, okay, elastic part, viscous part, then there is a evolution equation. Then some people say, oh, what is the elastic part? Is it phenomenological or micromechanical? Some people say, oh, do you like the Ogden approach, X approach? There are a lot of debates, a lot of review papers, a lot of paper in the hyperelasticity and viscoelasticity community. But my point is, it's not about micromechanics, it's not about phenomenology. My point is how I can capture the data with a minimum amount of parameters that will give me unique parameters so that I can validate. So that was the challenge. So I was discussing with my friend in Portsmouth. He said, okay, can we do something, better modeling, not with the evolution equation. At least we can capture the rate-dependent data, because most of the polymer will show you rate dependency, strain rate dependency. So let's capture the rate-dependent data with a very simplified model. Then he said, Mokarram, I have a hyperelastic model that has 4 material parameters, okay? N, capital N, alpha, and what about this, and mu. It's an excellent model. Okay, fine. So we take this model as a hyperelastic model, right? Because this is the same material. So if a material fits well with the hyperelasticity, basically the same model should give you the rate dependency of the same material, right? Why not? So what is the idea? So I said, okay, can we play with the parameters? Right? So I did my PhD in curing phenomena, which is basically a time-dependent phenomena where the material becomes stiffer and stiffer and stiffer. So material is changing with respect to time. Curing means if you take a liquid and it will become solid during the transformation from liquid to solid. That is called cross-linking or polymer curing process. You start the journey, and then the main philosophy here, now the parameters that you see mu, n, alpha, and small n is no longer depend on, it's no longer on constant. It depends on strain rate. Why strain rate? Because during the experiment, I realized, oh, what I'm doing, I'm prescribing the strain rate in my machine. I said, hey machine, please go from here to here in a certain time. So that means I'm prescribing a strain rate in the machine. So that I know. That is a given parameter. Right? In the experimental case, I'm always giving the strain rate to do the, whether it's rate dependency or the relaxation, multi-stage or single stage, I'm always pulling at a certain rate. Okay? And I'm observing other phenomena. So that means the strain rate is a given parameter. Now I want to take this parameter and then I want to set a function of this parameter, strain rate, to get the parameter that appears in the constitutive model. Okay, so fine. So now the constitutive model becomes like this. So it depends on strain rate, epsilon dot, right? That I know before the experiment. Before starting the experiment, I know at what strain rate I will do the experiment. So this is a given parameter. It's not unknown.
So epsilon is the linearized strain?
Linear strain or non-linear doesn't matter. I mean, here you are giving basically a strain rate. Yeah, linear strain in that sense, yes. So epsilon is lambda plus 1. Okay, so we're happy because this paper at the end published in GMPS last year or 2 years ago. So here, and then we also have observed in the experimental data, you can see that almost all data has some sort of permanent set. That means if you go and if you want to come back, it doesn't go to the 0 position, right? So there is some sort of permanent set. Whether it will recover or unrecover doesn't matter. There will be some sort of permanent deformation. So we need to take into account that one as well during the modeling phase. So we look into the literature, and classically, you know, the people did it so-called Marlin's damage and permanent or recoverable or whatever. We are not interested. We just take the traditional recipe by Ogden and Dortman and so on. So now we have the strain energy that depends on a damage factor plus some residual. This is classical. There is no innovation here, okay? So, and then now the model takes into account the damage, and that will give you extra 3 parameter. But you know, in comparison with the existing literature, people use 5. For example, Kim Hu, the guy you know, he has his own Marlin's effect model, the micromechanical base and so on. He has a couple of parameters. So here we have only 3 parameters, B, C, and we have kappa. So 3 parameters additional. So 4 parameters for hyperelasticity, 3 more parameters to include damage. Okay, fine. So now we have 7 parameters that include hyperelasticity and damage. But please keep in mind, up to now, we're not talking about strain rate. And now if you compare with the hyperelastic damage model with the literature, we are within the range. Most people use 9, 10 parameters to include the damage. We are in 7 or 5. Okay. But here, now the recipe is, now all the parameters that I'm talking about now depend on strain rate. So now even this kappa now depends on epsilon dot. So all the 7 parameters that I have, if you say, okay, I don't want to, later I will show you the experiment validation. If you say, no, I'm not interested to model damage, okay, fine, only the rate dependency, that's fine. You don't need to take these 3 parameters and so on. And then the main point here, all parameters are depend on strain rate. So let's go to, because the experimental discussion. So everything more or less, if you look into the literature, 99% data are uniaxial, right? So I put the setup into uniaxial form, right? Homogeneous uniaxial form. That means other 2 directions, you have to do no constraint and yes, 0. So that will give you the lambda is lambda 1 is lambda, and lambda 2 and lambda 3 is, if you take into account the incompressible constraint, that is lambda 2 minus half, right? And this is the same for your damage variable. Okay, so I get all the parameters, the framework. So again, please keep in mind, I have 7 parameters: mu, n, alpha, small n, kappa, c, and b. These are the 7 parameters I have without considering the rate dependency. And if you have only hyperelasticity, even I don't care about, my mu, n, alpha, and small n is for hyperelastic parameter. If I take into account the damage, then there will be 3 examples. Now I'm talking about rate dependency. So now my function became, so the parameter becomes depend on lambda, right? Lambda dot, right? So here, what will be the simplest? Simplest one is the linear function, right? So we take into account, so that will give you extra 7 parameters. So what is the benefit? The model that I have shown you, the previously I tried to use, that has more than 18 parameters or 19 parameters. So now it comes down to 14 parameters. The question is, does it give you better fitting and validation? Okay, let's have a look. Okay, so now, sorry for going back. So what we did, we took 4 different set of data. Luckily, I'm proud that I had experimental data from different polymers in different years and so on. So this is one of the data that we published in 2000, quite complex data, in 2020, that's from nonlinear mechanics paper. So here you see the rate dependency, and this is hyperelastic data. So hyperelastic data. So what we did, we took the model and tried to fit this 3-stranded dependent data with permanent set. That means that will give you 14 data, so 14 parameters, right? This is fitting. Please don't confuse, because most of the papers I get for review, people do nice fitting. I say, what is the validation? You know, nice fitting. So what? What is the validation? Validation means show me that your model with the same set of parameter can predict with other data of the same material. Couple of data. Okay. So this is the same case. So I asked Afshin, can you do prediction? Yes. So this data is not here. It's a strain rate dependent data, and even it's beyond that deformation mode. It's 300%. This is 400%. But this data is not rate dependent data. You may ask, Mokarram, how do you get this hyperelastic data? Can you remember? I have the relaxation test. So I took that point of the relaxation test where there is no viscoelasticity. There is no time dependency. So this data is from that experiment. So this is purely hyperelastic data. So what I did, I identified and got 14 parameters. Nice fitting, you can see. You can get the R ratio and so on. And then, yeah, I will finish it in time. So 14 parameters and fine. But now I need to I need to validate the model. So I said, remove 10 parameters that belongs to permanent set or Malins effect, that belongs to rate dependency. So take only hyperelastic parameter. So I have 4 hyperelastic parameters, 1, 2, 3, 4. Right? Because I already got it from the previous setup. I use this and I try to predict this. It's nicely fit. Right? So this is one kind of validation. And it's not only within the range, it fits quite well beyond the range. This is the good thing of this modeling approach, because it's go up, down, and go up. That was the challenging from my previous model. And then, second set of data. This is a different data. That's 2012. And again, what we did, we fit the hyperelastic data. Please keep in mind, this is different data. It's not the same data, okay? This is from another polymer. That was 3D printed polymer. This was a PHB polymer from 3M. So we at first fit hyperelastic parameter with the hyperelastic data. And then only 4. Still, we have 10 parameters. So we try to fit rate-dependent data. It's a 2-strand rate that has quite good amount permanent set, and this is fitting. Now we have 14 parameters. Now I want to validate. So for validation, I need the data that was not included in the fitting. So I have now new data. New data means either high strand rate or low strand rate and different strand. And you can see these are the new data that was never used for the fitting. Very nicely fit. So I'm happy with the validation, right? Third set of parameter. Again, we did we use two set of data. One is the loading curve only for hyperelastic, unloading for permanent set. And once we have all the data, then we use for different strain rate to validate the model. Then also, the different strain rate, and it nicely validate the model. This is again a different paper and different, for example, I published another paper in additive manufacturing, it's 3D printed polymer. So finally, this is another experimental data. This is not my data. This is published by Wang and Chester a couple of years ago. And then it has not only one cycle has come back, and then again reloading and loading and reloading. The traditional Malins effect type of experiment. And you see, okay, so we feed the model with that, and we try to validate with, let's say, different data, either different strain rate, different strain rate or different strain, and it nicely, and even we can see, I think this is the high strain rate, and it nicely fits. Predict the data. So we are happy, but please keep in mind, this is the hyperelastic model proposed by Afshin, our group, and then we try to extend it to rate-dependency, but still a lot of work to be done to incorporate the relaxation and other phenomena. And it can capture wide range of experiments. So one model can capture experiment from different polymers. That was not the case, the model that I have shown you with the constant tau and so on. So I had to change the model and so on. So that motivates me to come up with more versatile model. So here it's a framework. So you can use, for example, that's why I in the summary I should say, this is a modeling framework rather than a model. So idea. So if you play with the strain rate, and if you fine-tune your parameters, that means hyperelastic parameters or permanent set parameters with the strain rate dependent parameters, you will get a strain rate, because when you are doing experiment, as an experimentalist, I know what is the strain rate. So I take it, I will ask my student, hey, what is the strain rate? This is, put it there, do the fitting, do the validation. So still, we have to do a lot of things, relaxation and the anisotropy as well. I think Afshin already extended for anisotropy. There's a couple of publications. Okay, so I will take a little bit time, couple of minutes, to do a little bit advertisement of my group. So we recently got an EPSSC grant, 1.25 million, working on a different area. It's a magnetoactive polymer. So magnetoactive polymer is basically, again, soft material, multifunctional material. So this is a polymer filled with magnetic particle, like your LCE, that can be, you have the mesozen and all these things that can be activated by light. So this is a polymer. It contains iron particle or other magneto-responsive particles. If you have the magnetic field to move. Okay? So that is a video. And there are a lot of applications recently in sub-robotics and so on, and especially in the drug delivery. So the idea of this project is, so for example, you have nowadays the brain stroke and all these things, and to remove the blood clot from the brain, the big companies are trying to use nanoscale, I don't know where, or some nanoscale robot that will go in particular locations and remove the blood clot. So here, one of the idea proposed by one guy in MIT, that instead of using classical nanowire, whether we can use more active nanowire that can be controlled from outside, and for example, using MRI or some magnetic device. But in order to, or nowadays, in sub-robotics, magnetoactive polymers is hugely somehow envisions for future applications, for example, jellyfish type robots, or some UAV and so on. So in that case, we found that the traditional fluid structure interaction framework or computational tool can't tackle this soft material with the coupled field. So the idea is my collaborator in Edinburgh Napier University will work on the FSI part, and I will work on the magneto-active part. That is the grant. So that will start in June. So if you know anyone who is very good in nonlinear continuum mechanics with programming skill, please let me know. I'm looking for PhD students as well as postdocs. Okay, thanks a lot.